Hello, my name is Brendan Smirbeck and I represent Acumentrics Inc. And I'm happy here to talk about a project that we're sponsoring with the 2020 and 2021 ELECOMP Capstone program. That project is Project FaultLine, one that we actually started last year and we're hoping to continue this year. Why? We know there's a lot more to get done. Last year's team of students was absolutely incredible and we put down the foundation of something that we think could be real big. Now, like I said, my name is Brendan Smirbeck. I'm a software engineer at Acumentrics. I've been there for several years. I've also been a technical director for Acumentrics and their projects with the ELECOMP program for a few years now. I started working at Acumentrics in 2017 following my own being on the Acumentrics project, developing a software application to interface with Acumentrics' core products. That, however, isn't really the focus. What I'm aiming to do today is talk about Acumentrics as a company as a brief overview. Then we're going to be looking at some previous year's projects. Trust me, they're relevant. And then we're going to go looking at the FaultLine project, what they accomplished, and how we can continue that for a second year. Now, Acumentrics is a trusted manufacturer of rugged and reliable power solutions. And these solutions are used across a multitude of industries. When we look at the first picture here, what we're seeing is a Predator B drone, and the people there are pilots at a ground control station. Behind every drone, there's at least one or two pilots, and behind every ground control station, there's an uninterruptible power supply. Now what that does, it just takes an input power source, conditions it, inverts it if it needs to, and it also charges a battery. So in the case of a power outage, that ground control station remains operational. Now, it doesn't just have to be in one of these stations. Our ground and mobile troops of many different branches of armed services also use our power products. But it isn't just, including the military. We also have people looking for these power products in like a rugged industrial environment. The reason why is that we create rugged solutions. These are products that are able to withstand hot and cold, blown precipitation. You can shoot at them with guns and they're just designed to continue working, because when that power is mission critical, you want to make sure you can trust the supply. Now, our capstone projects have varied throughout the years. I myself did a purely software project. We've had battery management systems, we've had that piece of software, but in 2018 we had the Smart PDU. This was a power distribution unit that was intelligent. Now, a power distribution unit, in all intents and purposes, is a glorified power strip. It has an input, a source, and it distributes that among output receptacles. We tasked the students with saying, hey, make it smart. And lo and behold, they did. The project placed second at the ELECOMP Capstone Summit, and I can happily say that their product is going to be commercially available really, really soon. As a project lead, we've been taking what their project was, the prototype, the software, we've been revamping it, giving it new features, new functionality so that our users and our customers will get the most from it. Also, Mike Modulani, he's going to be another technical director. He was hired from that project team. We liked his work and said, hey, you want to keep working on it? So that, while it isn't completely related, will come back. What I'd like to talk about is FaultLine. Now, FaultLine was a project that I tried to get sponsored for several years. If you want to see some more background as to how this project came to be, there's a project proposal video on the ELECOMP YouTube channel in which I dive a lot more in depth with the theory and what actually brought us to the point where we had the first project. So I'm just going to summarize it a little bit. We look at these products, electrical devices, and they have characteristics, identifiable ones. Now, this doesn't involve putting a sensor inside. It doesn't involve, breaking it open after you buy it and logging. It's just simply how it consumes power. Now, both computer and electrical engineers, you should have seen this and know what it is very well. It's the power triangle, where we can see our active, reactive, and apparent power. Knowing the phase angle, we can derive the power factor, which gives us a little bit more insight. And as we look into the frequency domain, we can also start analyzing the both voltage and current signal waveforms as they're affected by harmonics. How do these signals get transformed by characteristics at those higher harmonics? But what this does Essentially, it gives us a power signature. Think of it as a fingerprint that describes the product. And what we focus on is getting that power signature of a working and functional product. Now, once we know what a functional product is, when it doesn't act the same way, i.e. when the power signature changes, then we can have a clear indication that something might be wrong. And this can be extremely helpful. Specifically, when we're looking at fault prediction, we're looking at these kind of electromechanical devices because their failures can sometimes be gradual. Once we can see that we're starting to get a mistake, for instance, with that fan right there, it has an induction motor, and it has some known ways that that motor fails that can actually be seen when we're looking at that electrical signal. Now, we're not inside of it, we're just monitoring voltage and current outside of the device. But when we start to see that first sign, we can tell the user, hey, something might be broken. It might be worth it to go check it out. Because it's much better to see the induction motor is starting to fail and either removing the product and putting in a replacement or repairing it, then let's imagine this fan is not just a small desk fan, but is, 20 feet tall. If a blade flies off or that blows up, it's going to cause a lot of damage, i.e. catastrophic failure. The idea is that by learning, key on learning, we're talking about machine learning here, that we can accurately model what a good device is, and we can predict when it's going to fail. This is predictive maintenance and fault detection. That is the core of the FaultLine project. The students weren't told what device to use, how to collect data, or anything, but I can tell you that their project was a complete success. What you see there is the prototype of their FDU. The FDU stands for Fault Detection Unit. Now, what it is a device right here that is able to infer based on real-time data whether or not the fan that's plugged into it is operating correctly or if it's failed. And if it has failed, in what way? We'll dive into it a little bit more, but you can see here we have a custom designed printed circuit board and we have a ribbon cable connecting to a microcontroller, in this case a Raspberry Pi 4. There's also some LED indicator lights just for visual indication. If you plug in a good fan, you get a green light. If you plug in a faulty fan, if it knows what the fault condition is, one of the other lights will turn on, or if it doesn't know and it says it's just a general fault, a last light will turn on that says, hey, something's wrong, I don't know what it is. This was a success, as I said. As you can see also, based on the size of a Raspberry Pi, which is more or less the size of a phone, it's pretty small. This isn't a big build. And we think that there should be more to this. We have to take this idea and develop it further. And the best way for us to do that is look further. What can we do? Should we continue working with fans? Should we try to work with any device? Well, we already have a couple steps. The first of which is actually something that was developed by another one of our computer engineers on the team, Brianna McDonald. Now, our initial machine learning model simply just used, RMS current, RMS voltage, looked at instant, power as an aggregate, and kind of had this prediction mode that worked. Absolutely worked. But we didn't go into the frequency domain. So we already have a model designed by Brianna that works. It does have some quirks. It needs to be, reviewed, revised, and otherwise made more efficient. But that's one angle we could go in. That's more deeper into the theoretical, deeper into, making this work. That's where the brains come in. But we have a bigger problem that we have to answer. We can't sell a custom PCB and a Raspberry Pi plugged in with a ribbon cable and say, here you go, figure it out. It needs to be integrated. And that's what we're hoping to do, is actually integrate the fault detection unit into our smart power distribution unit. The reason why is that smart PDU uses a very similar chip to do its metering. It's using a microcontroller on which the code from the Raspberry Pi would likely work. There might have to be a couple little changes, but nothing too major. And lastly, it's the most simple. There isn't any conditioning really happening. It doesn't have an inverter to convert AC to DC or vice versa. There's no batteries to charge. It is, like we said, a glorified power strip. So that being said, that is our goal. We're asking a team of students to take what the previous team has already developed, the prototype, the models, and teams of years past, the PDU, and put them together. Prove that this FaultLine project is not just a proof of concept, and it actually has a marketable, viable, application within the smart PDU. Now, that being said, I'm going to briefly talk about the smart PDU itself, of which I keep on pointing over there. It's because I have the guts of one of them right here. Also have some prototypes, but shh. So, the smart PDU. It is a lovely device. And basically, like I said, it takes an AC input. It has a number of connected devices, but it can also be smart. It can communicate. It has an application, a web application. To those who know it, it's React. We love React. And basically allows you through a smartphone, tablet, desktop, laptop, any device with a web browser, connect to, monitor, and control your PDU. It has an OLED display that you can also drive physically, and it can also communicate with our core products, those UPSs, using the SNMP. SNMP is the Simple Network Management Protocol. It's pretty much standard. The fault detection unit, in contrast, we're going to dive in a little bit more now, is relatively simple as well. It has a supply, and it also has an input for the appliance. So we supply the board with power, and we plug in our appliance. Let's say it's a fan. Using current transformers and sense resistors, we're able to get an idea of what's exactly going on. That chip right there, the ADE7880, is responsible for all the metering. The Raspberry Pi communicates with the chip and gets the data in real time. And then we have our output LEDs, which are just used as a means of creating some visual indication. Now, there are some parts missing here. Because of the Raspberry Pi's low processing power, there's a step that was left out. That is training the model. Training a machine learning model needs a lot of input data and some beefy processing power, or a lot of time. Now, we've chosen a single board computer for the smart PDU, which is actually geared towards machine learning and AI applications, meaning that it has some more power. Can we do training of the model within the smart PDU? We're going to have to find that out. But in this case, the model was already trained. It's simply performing inference, which is when it takes real-time data, runs it through the model, and sees what the output is. Now, with that being said, we should probably get starting to look at some of these tasks. Now, for anybody looking at this project, it is going to be tough. It asks a lot. More so this year because the models have already been developed, so we need to go a little bit further. As such, there's tasks for both computer and electrical engineers. As always, I'm going to ask that students complete an introductory course on machine learning. This is simply so we can get a background into what we're doing. There are some specifics used in our current model that we're going to ask students to also familiarize themselves with. That being LTSM, long-term short memory, the basic fundamentals of a recurrent neural network, and just the principles behind harmonic analysis, that being for that new model that we have developed. Now, computer engineers, you can shut your ears because we're going to next talk about our electrical tasks. We need you to look at both the smart PDU as well as the fault detection unit and just get an understanding of how it works. The next, we'll have to actually see if it's possible. If you tell me it's not, well, cool, we'll have to change the PDU and make it work. That's when I say we'll be making changes to accommodate the FDU integration. Now, this will likely require some new boards, some changes to boards otherwise. So if you have a background in, designing PCBs, or you're taking Mike Smith's PCB design course, that's always a plus. And of course, what's really important is making sure that after these changes have been made, it's all verified. Now, my CPEs, you have a lot to do. Naturally, it's a machine learning project. Now, what we're going to ask you to do is basically gain an understanding of how we already communicate with the metering chip inside of the PDU, how we're logging data, how we're controlling the relays, and to some level, the mammoth of the whole thing, the application, that web app. It's not going to be too much of a focus. However, we need you to learn it. Then we're going to look at the FDU. And for you, this is going to be learning the models. Why did we choose our layers? How are we working on this? How are we able to do what we say we're able to do? How are we training, and how are we performing inference? We then need to take that prototype, find some way to mix or change it, and shove it in the PDU. After that, it's going to be measuring, proving that it works, improving on the model if we have time, and showing that if we can train the model using the PDU, and that doesn't have to be performed on a different device. That being said, we look at our requirements. Now, some projects have crazy requirements. You need 10 years of experience on something that's only been out for 5. I do have the meat and potatoes, the rough ones here, but congrats. If you've made it this far in your careers as students, you have all of the requirements. You've taken the ELE courses, you've taken the math courses, you've taken the CSC courses. So what's really going to stand out for a candidate is if you have some background in some of the other aspects. Have you worked with machine learning before? Have you used BeagleBones or Raspberry Pis? Do you know how to use web apps? Is this something that's your wheelhouse and I'm basically just describing what your hobby project is? That's ideal. That's what we want. We want people who are aware of the challenge and the rigor of the project and are ready to get started today. And if you want to get started today, what I'd recommend is Google has what they call a crash course in machine learning. It's entirely driven online. You don't need to download any software. And what it'll do is give you the background, really the fundamentals as to, what are vectors? What is our inference? What is our output? What are these layers that we're trying to deal with? How do we, modify the hyperparameters? If this sounds like anything you've heard, great, you have a background. If I'm speaking Greek, well then, that's probably a good idea. Now, with that being said, I am looking so forward to this project. I do believe that this project will change the world. It can be used absolutely anywhere. Anywhere where there's something plugged in and powered, this technology can be implemented. And based on recent publications and what other universities are doing, MIT, for example, I think the world is getting interested in this, and the world is trying to find an application. All I'm asking is that it's from URI students. That all being said, I just want to thank you for listening, and good luck.